Welcome to the CERIAS seminar for February 3rd. Today I'm pleased to introduce our own Professor Hemanta Maji, who has just joined the Computer Science Department in CERIAS this last fall. He comes to us from the university, doing a postdoc at the University of California in Los Angeles. So you might think this winter is being a shock for him. However, before that, he was at the University of Illinois, so this is almost like coming back home for him. And so with that, I will turn it over to Professor Maji.
So today I will be talking about how to securely compute, but robustly. Okay? Before I move ahead, I want to give a very intuitive summary of what secure computation means. I'm going to use a couple of examples to explain what the intuition behind secure computation is. So recently, Alison and I created profiles on Tinder, and it turned out that we were a match. She was happy that we finally met, but I worry. I worry because Tinder knows that we are a match. And in fact, Tinder knows something more. Tinder knows our complete profiles. So my main concern here is that Tinder can use this information to spam me with targeted advertisements. Ideally, I would like to perform matchmaking such that the privacy of the members is intact. In this example, you might think that privacy is not mandatory. It's sort of a luxury. In the next example, it will become clear that it is mandated by law. Suppose there are a large number of hospitals, each with some patient medical histories, and a researcher is interested in finding out whether there exists a correlation between smoking and early onset of Alzheimer's disease. Hospitals cannot pool together their medical histories at one place where this scientist can test his hypothesis. So, is there a way that we can test this hypothesis while maintaining the privacy of each individual patient history? In this case, note that privacy is not optional. It is mandatory by law. In similar vein, let's consider another example. Abby came across a DNA sample at a crime scene. She wants to run a DNA match with respect to large number of samples stored at different DNA databanks, for example, at the federal, state, or the local level. All these databanks are mutually distrusting. So the only way she can run this match is by sending the sample to each of these databanks, and they run the match on her behalf, and then they report back with the result. Now consider the case that this sample belongs to someone who is innocent. What has happened is that we have created copies of this innocent person's DNA at each of these DNA databanks without prior consent of this person. So the question here is, can we perform DNA matching while preserving the privacy of innocent people? In these examples, we saw that sometimes privacy seems like a luxury, sometimes it is mandated by law, sometimes national security depends on it. Suppose we know that there are a large number of satellites orbiting Earth. Sometimes they run into each other, and this destroys these satellites completely. So what we would like to know is that, is there a chance that our satellites are going to run into each other? So consider the following example. There are multiple countries, each having multiple military satellites, and they want to find out whether there is a risk of collision in next 2 hours. The question here is, can we perform collision detection without revealing the location and the trajectory of the military satellites? So one way to formulate the problem and perform computation securely is as follows. We have large number of parties. Each of them hold secret input x1, x2 up till xn, and they have a common trusted party. What they do is that they transmit their inputs to this common trusted party, who performs the computation on their behalf and replies back with the computed outcome. Many secure computation is performed in this manner. But note that this common trusted party is a single point of failure and an attractive target for attacks. If if the privacy of this trusted party is relinquished, then the privacy of each of the parties is lost. Okay? Most interestingly, such a trusted party might not even exist. Consider the example of collision detection among military satellites. Do you believe that multiple countries are going to have a common entity into whom they are going to entrust their national secrets? No. So in reality, what happens is that we have multiple parties who have private inputs and they want to perform a computation. All they have is communication channels which allow them, every pair of them, to talk to each other. Okay? The aim here is to algorithmically emulate the trusted party. Okay? Now, secure computation guarantees that even if all but one of these parties are corrupted, that is, they are colluding and are being adversarial, the privacy of the honest party still remains intact. I want to emphasize here that the adversaries are insiders, that is, they are participating in the protocol itself. Contrast with the case of encryption, where you try to protect against outsider attacks. Okay? So secure computation, in some sense, provides extremely strong security guarantees. And as with all nice things in the world, we know that it is impossible to achieve. So is everything lost? What do we go henceforth? So if we have some cryptographic resources to begin with, then we can bootstrap this whole process and perform secure computation. So cryptographic resource could be something algorithmic, like computational hardness assumption. For example, we assume that factorization is hard, or AES is a function which is hard to invert. Or it could be something physical, like a trusted hardware or noisy channel. Using these kind of cryptographic resources, we know how to perform secure computation. In particular, in this talk, I will be talking about correlated private randomness. These are extremely strong and powerful cryptographic resources. These help us perform wide and diverse kind of secure computation. Let's, at an abstract level, they follow the following paradigm. You toss a random coin, large number of them in fact, and the first party gets a particular function evaluated on that random coin, and the second party gets a different function evaluated on the same random coin. Let's take two examples, which will be our running examples in this talk. Erasure channel performs the following. You toss large number of random coins. The first person gets all the coins. The second person gets the same coins, except that a third of them are erased. Okay? In binary symmetric channel, you toss large number of random coins. The first guy gets all those random coins, and the second person gets the same coins, except a random third of them are flipped. Okay? Using these cryptographic resources, we know how to perform secure computation. There is 3 decades of amazing research backing this problem. In these 30 years, we know how to perform secure computation, which provides extremely strong security guarantees against diverse kind of adversaries. So, is everything solved? No. There is a fundamental concern with all of these approaches. They assume the security of these protocols crucially hinges on the assumption that these cryptographic resources have no imperfections. But we know that in real world, this is false. How? Adversaries can perform power analysis or acoustic attacks on devices, or they can perform wiretap attacks on devices. Using these attacks, imperfections are introduced into these cryptographic resources, which can possibly lead to insecurity in the protocols. So now we are at a position where we can state our formal problem statement. It's very simple. Can we perform secure computation even when the cryptographic resources given to us are imperfect in nature? Okay? My research shows that yes, indeed we can. Okay? So to better understand the explicit problems that we encounter, let me explain how secure computation is performed. Initially, parties get together and compute the correlated private randomness. Then they store it locally for future use. And finally, they use it to compute a function securely. Note that an adversarial party can perform attacks like wiretap attacks, acoustic attacks in each of these phases on the correlations stored by the other party. These attacks introduce imperfections in the other party's correlations, and we want to perform secure computation despite these imperfections. Let's delve a bit further. Let me give some representative problem statements that we encounter. The first question that we try to answer is what kind of cryptographic resources suffice to perform general secure computation. We want to give an algorithmic characterization. Want to give an efficient algorithm which characterizes which form of cryptographic resources suffice to perform general secure computation. Not all cryptographic resources are useful. In fact, something like common randomness is useless for secure computation. The reason I give this example is because shared randomness is extremely useful for encryption. But remember, encryption only protects us from outsider attacks. Since secure computation has to protect against insider attacks, it turns out that common randomness is completely useless. Next, we try to find out how we can store the resources safely on our local disks, for example, so that tampering cannot be performed, or if tampering is in fact performed, we can recover from it. Another question is, suppose despite all these measures, some imperfections are indeed introduced. Can we salvage something out of it still? Okay? Finally, we want to find out how to efficiently use resources to perform a secure computation. We also want to understand whether weak platforms like cell phones, chip cards, can perform secure computation for us. And this technical part of the talk will deal with the last question here, where we try to perform secure computation even using imperfect cryptographic resources. So before I move to the technical part of my talk, let me try to place where my research lies among the various popular trends going on in cryptography currently. At a conceptual level, I try to visualize cryptographic primitives as two types. Either they are basic or more advanced. Mature companies like RSA use encryption to perform basic cryptographic tasks. Recently, there are startups like Voltage who use encryptions to perform advanced cryptographic tasks like identity-based encryption. On the other end of the axis, we have new startups coming up like Dyadic, which perform basic cryptographic tasks using secure computation. I envision my research at the other end of the spectrum, where I use secure computation to perform advanced cryptographic tasks. And I envision that in 10 to 15 years, this field will be fertile enough and strong enough to support startups. With that background, let's go into the technical part of the talk. Let me try to show you how we can perform secure computation. So let me introduce what the protagonist of the technical part of this talk is. It's called Oblivious transfer, or OT. It was introduced in 1985 by Ivan Goldreich-Lempel. It's an extremely simple primitive between two parties. We have a sender and a receiver. Sender has two bits, x0, x1, and the receiver has one bit, c. the receiver obtains output x sub c. Note that from perspective of the sender, the bit c is hidden, and from perspective of the receiver, the bit x 1 minus c remains hidden. Okay? So these two are the security guarantees of oblivious transfer. This extremely simple cryptographic primitive turns out to be extremely useful. It suffices for general secure computation. So if I want to perform general secure computation, all I need to do is realize large number of oblivious transfer instances. Now let me give an example of an imperfect cryptographic resource. Suppose I want to use my cell phone to perform secure computation. I can use my cell phone as a transmitter and transmit a sequence of bits. Since my cell phone is a weak receiver, not all bits are received. Some bits are erased. Say, a third of them are erased. But an adversarial receiver can install a larger antenna. Now, only a sixth of the bits are erased. What this adversarial receiver achieves is that this person is able to make the communication more reliable, unbeknown to the sender. Okay? This could possibly violate the security of a protocol which is using the cell phones as a cryptographic resource. There has been a lot of research which tries to implement secure computation from imperfect cryptographic resources. Let me give a glimpse of what's going on. This 25 years of research showed that we can do secure computation if our resource satisfies certain constraints. The result I'm going to present will directly increase this set of feasible solutions to a significantly larger set. How to interpret this graph? It will come at the end of the technical talk. So let me try to explain what an imperfect erasure channel is. In an erasure channel, the sender sends a bit B. The receiver either receives the bit B or the symbol bot. If the receiver is honest, then the symbol is erased with probability 1/3. If the receiver is adversarial, then the bit is dropped only with probability 1/6. Note that the sender doesn't know whether the bit is dropped or not, and the receiver doesn't know the original bit if it receives the symbol bot. Okay? Starting from this, we want to implement oblivious transfer, because we know oblivious transfer suffices to perform secure computation. In fact, I will show you how to implement only one copy of oblivious transfer, because there exists techniques which can take this qualitative result and transfer it into a quantitative result. That is a protocol which produces one oblivious transfer. We can construct another protocol which constructs oblivious transfers, large number of them, at good rate. So our goal is to come up with a protocol which takes input x0, x1 from the sender and bit c from the receiver and provides x sub c to the receiver. The privacy should ensure that sender should not be able to guess the bit c, and the receiver should not be able to guess the bit x 1 minus c. Let me go ahead and give an example protocol. First disclaimer, this protocol is a very old and famous protocol. What's new is our perspective as to why it works. And then we'll extend it to more general imperfect resources. So the sender sends large number of bits through the erasure channel. The receiver receives these bits, and a third of them are erased. So these black circles represents that the bit has been erased. Now, for purpose of this protocol, let us assume that the choice bit c is 0. What the receiver does is that it randomly partitions the indices into two equal sets. Okay? In this case, two sets of size 3, such that the first set contains indices which were all received. For example, it can do the following. It creates the first set as 1, 0, and 3, corresponding to bit B1, B0, B3 because they were received. And every other index is put into the other set. Okay? Now he sends these indices to the sender. the sender sees that the first set is 103, so he expresses x0 as b1 plus b0 plus b3 plus the bit r0. It sees that the second set is 245, so it expresses x1 as b2 plus b4 plus b5 and the bit r1, and sends these two bits r0, r1 to the receiver. Now note that the receiver has r0, receiver has b1, b0, b3, so it can just add them and recover x0. Okay? This is the protocol. If C was 1, the receiver would have swapped these two sets, and it would have received x1. Clear? Now let me argue why this protocol is secure. From the sender's perspective, all it sees is these two sets. This is completely independent of the sets of the bit C, because it is just a random equipartition of the original set. So C is completely hidden from the sender. Okay? Now let's consider the case when the receiver is adversarial and is trying to figure out the other bit x1 minus C. Recall that an adversarial receiver can make the channel more reliable. So some of the erased symbols turn out to be received. Okay? But still, a sixth of them are erased. In particular, b5 remains erased. So let us trace where b5 goes. b5 goes into the second set. So let's look at the recovery of x sub 1 minus C. This bit b5 is perfectly hidden from the receiver. So this sum remains perfectly hidden from the receiver. Therefore, it has no clue about the other bit. This simple protocol realizes oblivious transfer, and it's a very well-known protocol. Let's step back and try to understand why exactly it worked. To explain that, I need to introduce the notion of capacity of a channel. Oh, sorry, let me first summarize what we have proven. We have proven that if we have an imperfect erasure channel, where the erasure, yeah?
So I have a question. How did you come up with the figures of 1 by 6 and 1 by 3?
It's a general thing. It will work for all alpha beta less than half. That's the theorem. It will work for all beta less than alpha less than half, because you need to receive at least half of the bits, so to construct one of the set completely. So if the imperfect erasure channel...
So those were just, the choice of 1/3 and 1/6 were
Yes.
just for example then?
Yeah, for example purposes. The general theorem is this, what I'm going to state next.
Okay.
So if the erasure probability is alpha for the honest receiver, and for beta it is something less than alpha for the adversarial receiver, then what I have shown is that we can construct oblivious transfer if alpha and beta is less than half. Using existing error correcting codes, we can boost this half all the way to 1. I'm not going to talk about that in this talk. Now let us try to understand why exactly this protocol worked. So let me introduce the notion of capacity of a channel. Intuitively, a capacity of a channel represents the amount of information that an output symbol carries about the input symbol. If, for example, you consider a message forwarding channel, which always forwards the received bit to the receiver, then it has capacity 1. If you have a channel which always deletes the input message, it has capacity 0. Now, let's try to step back and come up with a new graphical representation of an erasure channel. Remember, when you send 0 into an erasure channel, you either receive 0 or the special symbol bot. If you send 1, you receive 1 or bot. This graph is graphical representation of the erasure channel. Similarly, we can draw a graphical representation of a message forwarding channel. If you send 0, you always get 0. If you send 1, you always get 1. You can also construct a graph for a message erasure channel. When you send 0 or 1, doesn't matter, you always get bot. Note that the first graph can be written as a convex linear combination of these two graphs, where epsilon is the probability of erasure. Okay? Now, what we have done is that we have expressed our original graph into as a convex linear combination of two different graphs. the capacity of message forwarding channel is 1 and the capacity of the message erasure channel is 0. Consequently, the capacity of the erasure channel is 1 minus epsilon, where epsilon is the erasure probability. Again, let's try to summarize what we have done till now. We have come up with a graphical representation of our channel. We have broken it up as a convex linear combination of component subchannels such that the capacities of these subchannels are diverse. They are very different. Okay? In particular, what we have achieved is the following. The highest subchannel capacity in the honest receiver case is 1. Okay? And the average subchannel capacity in the adversarial receiver case is 1 minus epsilon, where epsilon is beta. We can show that the reason our protocol worked is because there is a constant gap between these two numbers. Okay? I want to emphasize, we are looking at the best subchannel capacity in the honest receiver case and comparing it with the average adversarial subchannel capacity. We are not comparing the best with the best or average with the average. That will, in that case, this capacity can never surpass this. The only reason that this happens is because we are comparing the best in the honest receiver case with the average of the adversarial case. So this is the lesson that we have learned, that if we can achieve this, then we can construct oblivious transfer. So let's go to the main problem that we want to solve. Let's consider a binary symmetric channel. In a binary symmetric channel, the sender provides the input bit B, and the receiver receives the bit B or the flipped bit. And the bit is flipped with probability 1/3 if the receiver is honest, and if the receiver is adversarial, it is flipped with less probability. The channel is more reliable. In general, in this case, note that the receiver and the sender both do not know whether the bit has been flipped or not. In general, an imperfect binary symmetric channel is defined by two flip probabilities, alpha and beta, where alpha is the honest receiver flip probability and beta is the adversarial receiver flip probability. And the question we want to ask, for which values of alpha beta can we construct oblivious transfer? So let us try to apply what we have learned till now. This is a graph of binary symmetric channel, because given 0, we either get 0 or 1. Given 1, we get 0 or 1. The first thing that we want to do is break this graph into subchannels with very different capacities. This is not clear how to do in this case. We do not know how to break this one. To do this, we applied a trick. To send a message 0, I do not send 0. I send, let's say, 2 copies of 0. To send 1, I send 2 copies of 1 through 2 copies of the binary symmetric channel. What happens is that the receiver receives one of these 4 binary strings as its output. If the outputs are 0, 0 or 1, 1, it can be interpreted as output of a different binary symmetric channel. And in this case, it can be interpreted as output of a message erasure channel. So what we have done is that we have expressed our original channel as convex linear combination of these two subchannels. Note that this has capacity 0 and this has capacity higher than the original channel. Okay? So we have achieved our first goal. We have a good thing going, right? We were able to decompose it for 2 repetitions. Why stop at that? When we have a good thing going, let's keep it going. So why not try it for 3? That is, to send 0, I send 0, 0, 0. To send 1, I send 1, 1, 1. Again, we send this through 3 copies of binary symmetric channel, and now the receiver obtains 1 out of these 8 binary strings. The first 2 can be seen as output of a particular binary symmetric channel. The last 2 sets can be seen as output of a different binary symmetric channel. What we can show is that this has capacity less than that, and this has capacity higher than that. So again, what we have achieved is that we are able to express our original channel as convex linear combination of component subchannels with diverse capacities. But have we achieved our second goal? Is the maximum honest subchannel capacity higher than the average adversarial subchannel capacity. Let me explain how to achieve that using the case alpha equal to 1/3 and beta equal to 1/6. This is just for example purposes. Okay? I will prove it using pictures. Initially, when I'm sending 0 as 0 and 1 as 1, there are two channels. The green channel, the green rectangle represents the capacity in the honest receiver case, and the blue rectangle represents the malicious capacity, capacity in the malicious receiver case. Suppose we use codes of length 2, then there are two subchannels, one with this much capacity and another with this much capacity. In the adversarial case, we have one with this much capacity and another with this much capacity. This is the highest subchannel capacity in the honest case, and this is the average malicious capacity. Note.
Can you define the axes?
This is the probability with which a particular subchannel occurs.
Come again, sorry.
This is the probability with which a particular subchannel is sampled. Like what are the convex coefficients in the convex combination? So for example, earlier it was 1 minus epsilon epsilon. So we are defining these numbers now in the case of binary symmetric channel. So there are two.
One is the
capacity.
successful channel, one is the...
One is the adversarial channel, one is the blue are the adversarial channels, green are the honest channels.
Yeah.
And there are two channels here, one of this much and another of capacity 0 actually.
Yeah.
It will become clear in the next picture actually. Let me just show the next picture. It has codes of length 3, and now you see that there are two channels in the honest, two sub-channels in the honest case and two sub-channels in the adversarial case. And we are comparing the average adversarial capacity with the best honest capacity. Note that both of these are rising, but they are getting closer to each other. Okay? If we use encoding schemes of longer and longer length, they keep getting closer to each other, and finally at length 7, the honest subchannel surpasses the average. Okay? At this point we say that capacity inversion has taken place. So the summary here is that we can use codes of length 7 and capacity inversion will be realized. At that point we can construct oblivious transfer out of it. This is the whole summary. So for what values of alpha and beta does capacity inversion happen? Let me explain that using pictures. So on the x-axis we have beta, on the y-axis we have alpha. When we use codes of length 1, we never experience capacity inversion. If we decide to use encoding schemes of length 2, then a small feasible region comes to life. Let me explain what that feasible region is. Suppose beta is 0.1. In that case, this green region is the set of all alpha which exhibit capacity inversion with respect to this particular beta. Okay? So let's use codes of length 2. Then this region keeps on increasing, and it tends to a limit curve. So what we can show is that if your alpha and beta lie below this limit curve, then capacity inversion happens and we can implement oblivious transfer. Let's take an example. Suppose the best antenna in the market that is available has only 5% probability of error. Then we can construct oblivious transfer when an honest person is only using a weak receiver that has 30% chance of error. Okay? Alternately, if the best antenna in the market is 95% accurate, then we can still perform secure computation, assuming that the honest person is using a 70% accurate cell phone. Okay? This is the theorem that we obtain. If alpha beta is bounded by limit beta, then we can show how to construct oblivious transfer. In 25 years of research, we were able to get this small range of feasible parameters. In particular, if the best antenna in the market is 95% accurate, they needed honest people to have an antenna which is 86% accurate. Our method adds this huge space of new feasible parameters, and we only need to assume that honest person has access to a 70% accurate antenna. Can we go beyond it? We do not know. I will like to conjecture yes, and this is an obvious open problem which I think can be solved in short term. To conclude, let me give a slight idea of what my research vision is. My vision is to construct maximally resilient algorithmic solutions which have provable security guarantees. And I want these solutions to be practical. What does practical mean? I want the solutions to run linear or near linear time, and these solutions should be highly parallelizable. I want to construct these things in a modular fashion as wrappers, for example, so that if you apply my resilient wrapper to existing cryptographic solutions, then these solutions inherit the resilience. The kind of research I do creates large number of collaborative opportunities, especially with departments like computer science, maths, and electrical engineering. Let me explain some of these opportunities with 3 representative examples. I'm currently looking to construct universal trusted hardware that can provide arbitrary amount of security. What does it mean? If you want higher amount of security, you do not need to throw away your existing trusted hardware and install a larger one. You can have a universal trusted hardware which can help you provide arbitrary levels of security. Okay? Next, I'm also trying to construct physical sources of physical cryptographic resources such that even if some of them fail, I can still obtain useful cryptographic resources which can be used for secure computation. The kind of research I do has significant intersection with theoretical computer science. When I talked about tamper resilient codes, these are closely related to something called non-malleable codes, which in turn are closely related to something called non-malleable extractors, which have come to life and prominence in recent past. Further, when I said that I try to understand whether weak platforms can perform secure computation, I am talking about de-randomization techniques and how they can be ported to cryptography. Finally, when I say that I want to understand the minimum amount of resource needed to securely perform a particular task, this measure has a very close connection with circuit lower bounds. This has the potential of providing a new perspective into a very classical and hard problem. Finally, from information theory and error correcting codes, the kind of work I do has imports or translates several classical information theory results into crypto. For example, in the results that I mentioned in the talk today, they crucially rely on translating Shannon's coding theorem into cryptographic perspective. Finally, I also design, all these protocols rely on design of error correcting codes, in particular algebraic geometric codes, which have certain properties. If you know, they are known as multiplication friendly secret sharing schemes. So if they exhibit these properties, then I can use them into my protocols. To summarize, I'm a theoretical cryptographer, and I like to discover truths of nature by studying cryptography through the lens of mathematics. And my aim is to design practical and provably secure protocols. And the kind of research I perform generates significant collaborative opportunities with diverse fields in departments like computer science, electrical engineering, and mathematics. To conclude, I would like to thank all my collaborators who made this journey and research extremely pleasant and fun. And thank you all for patiently listening. Yes?
So,
go ahead, there's a microphone. Yeah, thank you.
Push this?
yeah, it's okay.
Okay. So the
research that you've done mostly, does it account for the fact that the error correcting codes themselves are improving all the time, and even they stand at the cusp of a possible revolution with the influx of, say, quantum computation? I mean, if that happens, then seven bits is pretty less, right?
So, so the kind of the first layer of result which we are showing is a feasibility result of sort. Okay, efficiency improvements is a second order thing which can be achieved. In particular, we do not need explicit codes. We can work with random codes. So it is, I do not see a direct way of motivating a particular class of codes being useful or new improvements being useful in this particular problem. I think random codes can perform the work.
So I'm looking at it from the point of an adversary.
Yes.
So as the efficiency of your error correcting codes increases, so even if there is erasure in the bits, right? He can just assume a certain bit. He can just artificially construct a bit, and can't they just error correct through it?
No, because think of it in this way. What happens is that there are two channels, right? One is the honest channel, which has a higher capacity than the adversarial average channel, which is lower. So what we are going to do is push information at a rate which is intermediate to this two.
Okay.
So the honest person will be able to decode at least one channel, and the adversary will lose out on at least one channel. Just, it is a converse of coding theorem. You can do nothing to avoid it because information is being transmitted at a rate higher than the average rate. You just cannot avoid it.
Okay.
Shannon kicks in, basically.
I mean, I'm not a communication person.
I think a key thing here is how is it,
Yes.
is if you could just reiterate, why is it that
So
the honest channel were able to talk about the best rate, whereas the malicious party is only able to make or to talk about the average rate? Just to reiterate the intuition behind that. 'Cause I think
So
that's a key point.
let me give a like intuition where we actually started off. Okay, so think of it in this way: I'm going to send n messages. Okay, I only want the honest guy to listen to one message. He can ignore n minus 1. And the only guarantee I need is that the adversarial person doesn't get all the bits. He misses out on one of the bits. So there is an asymmetry in power. The honest guy listens to one channel only. The malicious guy can potentially listen to n minus 1 channels, but won't be able to listen to all channels. That's all we are wanting. Think of it in this way. Of the n bits transmitted, only 1 by n fraction reached the honest person, while 1 minus 1 by n reached the adversarial person. This is exactly the erasure channel that we had been talking about. That even if there is, for any values of alpha and beta, we can securely perform computation. This is the erasure channel.
So the key notion there then is that the honest party knows which bits it needs,
Yes.
the dishonest party doesn't.
So dishonest party knows what it needs, but it doesn't get everything, that's all.
Yeah.
So I'm sending, let's say 100 bits, honest person will get 1, the adversary will get at most 99. And this is sufficient to get oblivious transfer. He shouldn't get 100, that's all. If he gets 99, 98, we are fine.
Yeah, interesting talk. What I wanted to understand from this erasure channel, maybe that's a good example to look at, is that you assume that this channel has integrity in the sense that the adversary may get more information, but he cannot flip some bits.
Yes.
And you also make sure that there is no like adversary who is very close to the source and he gets all the bits.
Yes. So,
Some motivation, like, have you thought about like here is why this makes sense somewhere?
Let me answer the second question first. Like, suppose he gets all the bits. It is possible for a receiver to ensure that he gets all the bits. We know that cryptography is impossible in this case. So we cannot make that assumption at all. Like there is no hope of getting cryptography at that point.
Means you mean the cryptography impossible in the sense that universal composable security
No,
without random oracle, right?
No, nothing. Like OT is not possible. We are considering information theoretic security.
Yeah. Okay.
So, yeah. So the other thing was the way to think about it is that when you have receivers, they have thermal noise. Okay, even if you have a super cooled antenna, thermal noise is still creeping in, even if you are very close to the receiver. So there is a bound on how much you cannot be 100% reception. That's all I'm saying. That you can assume is the lower bound to the base channel. To answer your first question, when you are saying that whether it can flip the bits and things like that, it doesn't help, right? If I know I got the bit and then flip it, it doesn't help me. Whatever strategy I implemented, the sender is sending the bits. I can flip it in my mind as well, but doesn't give me any additional powers. It is simulatable, right? Like I receive the bit and flip it inside my head.
Yeah, I was thinking more like somebody who is a third person.
Oh, okay.
Yeah, but in the two-party case, indeed, it does not make sense for sure.
Yes. So here we are not trying to protect against an outsider. Yes, for a particular. Yes. And I just one comment, like these protocols that I mentioned are semi-honest secure, but they can be bootstrapped to like full security. We can do that.
Any other questions? No? Well, let's thank Professor Maji.